Welcome, everyone. So there are a number of places we could start when talking about higher degree polynomials, and by higher, we mean third degree, fourth degree, fifth degree, etc. But we already know about linear or first degree and second degree polynomials, so we're going to use that to start. And we are going to start with figuring out how many roots a polynomial could have. So let's start organizing ourselves. Let's create a little table. In this column, we will have the degree of the polynomial. We will write out a general equation, general form, I suppose, standard form if you want. What I'm also going to do is we're going to use what we know about factoring. To help us out here. And look like so. And we're also going to draw some pictures. Okay, there's a lot going on here, but we can figure this out. So let's consider a first degree polynomial, and that's gonna look like this: just ax to the first power plus b. This is also called a linear polynomial, but let's just stick with first, second, third degree, etc. Okay, so obviously, let's say most possible linear vectors. That's gonna be helpful in there. Whoop. Okie dokie. Well, it itself is already a linear vector, so there's only gonna be one. Remember, we spent a lot of time discussing the connection between the factors and the roots. And there's basically a one-to-one correspondence. So if there's one factor, there can only be one root. And this function would look like this. I know that this is a straight line with just one x-intercept. So it must look like this. Okay. Let's add this in here, by the way. This is not good phrasing. This should say the maximum possible factors. Maximum might be the same thing. Maximum number of linear vectors. Now I'll say max number of roots. Okie dokie, let us move on. If I have now a second degree polynomial, we have something that looks like this: ax squared bx to the first plus c. Now we know that this could have two factors, because that's what we know about factoring quadratics. And this will end up being 2 here, and therefore it could have two x-intercepts or two roots. And that would look like this. But that's not the only thing that could happen. Remember that if I take a parabola and just scooch it upward, eventually you'll get to this point where it looks like this, where your only x-intercept is also your vertex. So there's also the possibility for only one root. But if I were to keep going, I could have something like this, which has no x-intercepts, and so there could be 0 roots. Now, why doesn't this happen in a first degree polynomial? Well, notice that since there's only one x-intercept, and there must always be one x-intercept, no matter how far I take this line down, it's still gonna cross the x-axis somewhere. Quite interesting. Let us discuss now cubics, or third degree polynomials. Again, that's going to be something with an x cubed, and then something x squared plus something x plus something. Well, since the number of linear factors, each linear factor is x minus something, x minus something, x minus something. At most, they're going to be 3, because you'll have x times x times x to get your x cubed. So there will be 3 factors at most. Again, that would assume that this thing is absolutely, completely factorable. And we've seen problems like this. That would mean that there are at most 3 roots, and let's draw a graph of that then. I'm going to try to make this one a little bit bigger. Okay. So, if there are 3 roots, let's pretend the roots are right here. 1, 2, 3. If my graph starts this way, down here, pretend it could potentially start this way, but I'm just going to start off negative just because it's got to at some point hit that first x-intercept, and it has to curve back down to hit the second one, and then at some point it's got to turn around again to hit that third one, and then it must just keep going because it can't turn back around, otherwise there would be a 4th x-intercept, which is not what's going to happen here. But similar to how we played around with the parabola, we're going to play around with this cubic function by sliding it up or down. And so if I slide it up, eventually this little valley could just end up right here. Oops, sorry about that. Kappa. So you might end up with something like this. Something that has 1, and then just 2 x-intercepts like so. So there's the possibility to have just 2. If I were to raise it even more, I would get something like this, perhaps, where there is only now 1 x-intercept. And we had the same problem that we had with the first degree polynomial, where there's only this little tail is always going to be sticking off, and so you will never get rid of that 1 x-intercept. So you can't have none. There will always be at least 1. Quite PogChamp, in my opinion. Our last example that we are going to look at is a 4th degree polynomial. And again, that's going to be ax to the 4th, bx cubed, cx squared plus dx plus, I apologize, plus e. Since this is going to end up with an x to the 4th, this could have at most 4 linear factors, which would imply 4 roots, and let's draw that. I'm going to need some space, so we're going to draw this like so. So my first one in red will have 4 x-intercepts, so I'm just going to put them 1, 2, 3, 4. Just for the heck of it, I'm going to start negative again. And so I gotta hit that first one, come back down to hit the second, go back up to hit the third, come back down to hit the 4th. So I have this weird double mountain camel hump thingy. But let's move it around, and so if I keep again moving it upward, potentially see this. Let's go green. No, wait, magenta-ish color. And I'll have 1, 2, 3. Buggers. So that's definitely a possibility. I could potentially have 2, I think, as well, by going like this. 1, 2. Could I have only 1? This one's actually kind of interesting because I don't think I'm gonna have only 1 if I keep moving the graph upward. But if perhaps I move the graph down, I could maybe see something like this. By the way, I shouldn't have drawn it this way, but the humps aren't necessarily all the same size, so potentially one hump could be bigger than the other and you'll get that. And then finally, if I just move it down all the way, I could end up like this and just have no x-intercepts or roots. That was a doozy. So this is actually very interesting. I think it's quite clear that for any nth, and this is so important, we're going to put it in rainbows, for an nth degree polynomial, the maximum number of roots is n. We can see that right here. So an nth degree polynomial has at most n real roots. Okay. And secondly, observe that we couldn't pass. Oh my gosh, I am so sorry. Notice here, when n was equal to 2 or 4, we were able to get 0 real roots. Let me make this, put this in black here. We were able to get 0. Again, this is because the shape of the graph forces it to kind of come back on itself. Therefore, I think it's safe to say that the polynomial, if n is odd, then it must have at least 1. I should just scooch over here. Oh my god. Oh my god. At least 1 real root. And if n is even, it might have none. It might have no real roots. By the way, this is really important to say real here, and this will make more sense in the next couple videos. But hopefully this video was informative. I will catch you in the next one. Stay spicy.